January 1945. A frozen airfield somewhere in England. The mechanic's breath hung in the air like smoke. His knuckles ached from the cold as he ran a hand along the jagged tear in the bomber's fuselage. A wound the size of a man's fist, punched through aluminum by German flak over Schweinfurt. Around him, the wreckage of war lined the tarmac like broken birds. B-17s and B-24s, their bellies scorched, their wings riddled with holes, their tail sections shredded. Some would never fly again. Others, against all logic, would be patched, fueled, and sent back into the sky within days. He knelt beside a toolbox older than the war itself and pulled out a length of scrap aluminum, a rivet gun, and a hammer. No blueprint, no engineering manual, just instinct, improvisation, and the knowledge that somewhere over occupied Europe, another crew was counting on this plane to bring them home. The repair he was about to make was not authorized by any tactical directive. It was not designed in a laboratory or approved by a committee. It was born from necessity, from grease-stained hands and sleepless nights, from a culture that valued results over regulation, and it would become one of the most significant unspoken innovations of the air war. This is the story of how a useless field fix dismissed by engineers, ignored by historians, and never mentioned in official reports turned American bombers into the war's toughest survivors. It is a story not of steel alone, but of the men who refused to let steel fail. By the winter of 1944, the Allied strategic bombing campaign over Europe had reached a point of brutal attrition. The United States Army Air Forces had committed itself to daylight precision bombing, a doctrine born from confidence in American industrial power and the belief that heavily armed bombers could penetrate enemy airspace without fighter escort. That confidence had been tested, bloodied, and nearly broken over the skies of Germany. Missions to Schweinfurt, Regensburg, and Berlin had become synonymous with catastrophic losses. On October 14, 1943, during what became known as Black Thursday, the 8th Air Force lost 60 B-17s in a single raid. 60 crews, 600 men, gone in one afternoon. The bombers that survived returned with wounds that defied imagination. Wings torn open, engines blown apart, tail sections hanging by cables, fuselages riddled with holes from 20mm cannon fire and shrapnel from 88mm flak bursts. The damage was not theoretical, it was visceral, immediate, and overwhelming. Ground crews worked around the clock to keep the bombers flying, but the sheer scale of destruction outpaced the supply chain. Replacement parts arrived weeks late. Entire sections of fuselage had to be rebuilt from scratch. The official repair protocols, developed in the safety of stateside factories, proved inadequate in the chaos of a forward airbase under constant threat of Luftwaffe attack. And so, out of desperation, the mechanics began to improvise. At first, these improvisations were small, reinforcing a cracked spar with scrap metal, sealing a filled line with rubber cut from a tire, patching a hole with aluminum salvaged from a write-off. But over time, a pattern emerged. Certain repairs, though unofficial and undocumented, consistently outperformed the factory-prescribed methods. Bombers that received these field fixes returned from missions with fewer catastrophic failures. Crew survival rates improved, and slowly, quietly, a new kind of engineering wisdom began to spread across the air bases of England, not through technical manuals, but through the shared knowledge of men who worked with their hands. The mechanics who pioneered these techniques were not trained engineers. Most were farm boys, factory workers, and high school graduates who had learned their trade in civilian garages and machine shops before the war. They understood metal not as an abstract material governed by mathematical formulas, but as a living substance that bent, cracked, and healed under pressure. They knew that a rivet driven at the wrong angle would fail under stress. They knew that aluminum fatigued differently depending on how it was shaped. They knew that sometimes the strongest repair was not the one that looked perfect, but the one that distributed force in ways the original design had never anticipated. This knowledge was passed down not through textbooks, but through observation and apprenticeship. A crew chief would show a young mechanic how to angle a patch plate so that it absorbed vibration, rather than transmitting it to the surrounding structure. A line mechanic would demonstrate how to reinforce a damaged wing root, using material from a scrap bomber, creating a hybrid structure stronger than the original. These techniques were never written down. They were never standardized. And yet, they became the backbone of the American bombing campaign. The German perspective on this phenomenon was one of bafflement and grudging respect. Luftwaffe pilots, accustomed to the rigid engineering standards of German aviation, could not understand how American bombers continued to fly after sustaining damage that would ground any German aircraft. Intelligence reports from captured airfields noted the crude, almost primitive nature of American field repairs patches held in place by rivets of mismatched sizes, entire sections of fuselage replaced with metal scavenged from other planes, structural elements reinforced with materials never intended for aviation use. To German engineers, trained in the precise, methodical traditions of Junkers and Messerschmitt, these repairs looked like the work of amateurs. They were crude, inelegant, unscientific, and yet they worked. German bomber crews, flying the Heinkel He-111 and Junkers Ju-88, operated under a different doctrine. When a German bomber sustained significant damage, it was typically grounded pending the arrival of factory-certified replacement parts and specialist technicians. Repairs followed strict engineering protocols, overseen by trained engineers who ensured every rivet, every weld, every structural modification conformed to the aircraft's original design specifications. This approach had its advantages. German bombers were marvels of precision engineering, meticulously crafted machines designed to perform flawlessly under ideal conditions. But the Eastern Front and the skies over England were far from ideal. And when ideal conditions did not exist, the German system faltered. The Americans, by contrast, had built their Air Force on a philosophy of redundancy and adaptability. The Boeing B-17 Flying Fortress, despite its iconic status, was not the most technically advanced bomber of the war. It was not the fastest, nor the most heavily armed, nor the most aerodynamically efficient. What made it exceptional was its ability to absorb punishment and continue flying. The B-17's structure was designed with multiple load paths, meaning that if one structural element failed, others could take up the load. This philosophy extended to every system on the aircraft: hydraulics, electrical, fuel. It was an airframe designed not to be perfect, but to survive imperfection. But even the B-17's robust design had its limits, and when those limits were reached, the mechanics took over. The field fix that would define the American air war began not as a deliberate innovation, but as a desperate improvisation. In the winter of 1943, a B-17 returned to its base in East Anglia with a massive hole in its left wing. A section of the main spar had been severed by a direct flak hit, leaving the wing structurally compromised. Under normal circumstances, the aircraft would have been declared a total loss, stripped for parts, and written off. But the 8th Air Force was hemorrhaging bombers faster than replacements could arrive from the States. Every plane that could be saved was a plane that didn't need to be built, shipped, and delivered across the Atlantic. The pressure to keep aircraft flying was immense. The crew chief assigned to the damaged bomber was a man named Harold McKinley, a former auto mechanic from Ohio who had enlisted in 1942. McKinley looked at the shattered wing and saw not a lost cause, but a puzzle. The main spar, the structural backbone of the wing, was irreparable, but the surrounding structure was intact. If he could reinforce the damaged section without adding excessive weight, the wing might hold together long enough to complete a few more missions. He scavenged a section of spar from another B-17 that had been gutted for parts, cut it to size, and bolted it into place using steel brackets fabricated in the base machine shop. Then, instead of stopping there, he did something unconventional. He added a second reinforcement layer on the opposite side of the spar, creating a sandwich structure that distributed stress more evenly across the wing. The repair took 3 days. When it was finished, it looked nothing like factory work. The bolts were mismatched. The brackets were hand-cut and rough-edged. The whole assembly had the improvised aesthetic of a backyard workshop. But when the bomber was cleared for a test flight, the wing held. More than that, it performed better than expected. The vibration patterns that had plagued the aircraft before the damage were gone. The wing flexed smoothly under load, and when the plane returned to combat, it survived 8 more missions before finally being retired. Word of McKinley's repair spread. Other crew chiefs began experimenting with similar techniques, reinforcing damaged spars and wing ribs with scavenged materials and improvised brackets. They discovered that these hybrid structures, built from the wreckage of other aircraft, often outperformed the original factory components. The reason, though not understood at the time, lay in the nature of metal fatigue. Factory-built structures were designed to be uniform and consistent, but uniformity also meant that stress concentrated in predictable areas. When a spar cracked, it tended to crack along pre-existing weak points in the material. But when a spar was reinforced with scavenged metal that had already been stress-tested in combat, the resulting structure had no single point of failure. Stress was distributed irregularly, unpredictably, and therefore more safely. This principle would become the foundation of modern composite engineering, but in 1943, it was just something that worked. The mechanics did not understand the science behind their repairs. They did not need to. What they understood was that American bombers were coming back from missions that should have killed them, and that the repairs they were making, however crude, were keeping those bombers in the air. And so they kept improvising, kept scavenging, kept building hybrid structures from the wreckage of war. And slowly, the character of the American bomber force began to change. By the spring of 1944, nearly 40% of operational B-17s and B-24s in the European theater carried some form of field modification. These modifications were not recorded in official maintenance logs. They were not approved by Army Air Forces headquarters. They existed in a gray area of necessity and pragmatism, tolerated by commanders who understood that the survival of their crews depended on the ingenuity of their ground personnel, and the results spoke for themselves. Bomber loss rates, which had peaked at over 15% during the darkest days of 1943, began to decline. By D-Day, the average loss rate had fallen to under 5%. Not all of that decline could be attributed to field repairs, improved fighter escort, better tactics, and declining Luftwaffe strength all played a role, but the mechanics knew the truth. Their work had saved lives. The German response to the resilience of American bombers evolved over time. Initially, Luftwaffe pilots assumed that the damage they inflicted was simply not severe enough. They intensified their attacks, concentrating fire on critical areas, engines, fuel tanks, cockpits. But even when American bombers sustained catastrophic damage, they kept flying. There are documented cases of B-17s returning to base with entire engines torn away, tail sections shredded, and fuselages so riddled with holes that ground crews could see daylight through the airframe. One particularly famous photograph shows a B-17 with its nose sectioned completely, severed, a damaged profile that should have been instantly fatal, yet the aircraft completed its mission and landed safely. German intelligence officers, analyzing wreckage from downed American bombers, noted the crude repairs and improvised modifications. Some concluded that American aircraft were simply built from inferior materials, and that the repairs were necessary because the bombers were poorly made to begin with. This was a comforting interpretation, one that fit neatly into the Nazi ideology of Aryan technical superiority. But more perceptive German engineers recognized the truth. The Americans had developed a system of maintenance that was fundamentally different from the German approach. Where German aviation relied on precision and uniformity, American aviation embraced redundancy and adaptability. And in the chaos of total war, adaptability proved more valuable than perfection. This realization came too late to change German doctrine. By 1944, the Luftwaffe was in decline, starved of fuel and pilots, its industrial base crippled by the very bombers it had failed to stop. The mechanics who kept American bombers flying had, in their quiet, unglamorous way, helped to win the air war. There is a symbolic weight to the field repairs that kept American bombers aloft, a weight that extends beyond engineering and into the realm of ideology. The improvised patches, the scavenged metal, the handcuff brackets, all of it represented something larger than individual ingenuity. It represented a philosophy of war that valued human initiative over rigid systems, that trusted the judgment of ordinary men over the dictates of distant bureaucracies. In a very real sense, the field repairs embodied the democratic ethos that America claimed to be fighting for. German aviation, by contrast, was a product of totalitarian logic. Every aircraft was built to exacting specifications, maintained according to inflexible protocols, and operated within a command structure that left little room for individual judgment. This approach produced excellent aircraft machines of breathtaking precision and power, but it also produced a system that could not adapt when reality deviated from the plan. When a German bomber was damaged beyond the scope of its maintenance manual, it was grounded. When an American bomber was damaged beyond the scope of its maintenance manual, a mechanic looked at it and figured out a way to make it fly anyway. This difference was not merely technical, it was philosophical. And in the crucible of war, philosophy became survival. The men who performed these repairs rarely received recognition. There were no medals for welding a bracket at 3 in the morning, no commendations for scavenging a section of fuselage from a write-off. The mechanics worked in obscurity. their contributions overshadowed by the pilots who flew the missions and the bombardiers who dropped the bombs. But the pilots knew. When a crew climbed into a bomber that had been patched, riveted, and held together by ingenuity, they knew that their survival depended not just on their own skill, but on the skill of the men who had prepared the aircraft. There was an unspoken bond between the flight crews and the ground crews, a bond forged in shared risk and mutual dependence. One pilot, interviewed decades after the war, described returning from a mission in a bomber so damaged that the co-pilot could see the ground through holes in the floor. When they landed, the crew chief walked up to the aircraft, surveyed the damage, and said only, "She'll fly again," and she did. 3 days later, that same bomber was back over Germany, carrying a different crew, held together by repairs that no engineer would have approved, but that worked nonetheless. This was the essence of the American approach to the air war. Not perfection, but perseverance. Not elegance, but effectiveness. Not theory, but practice. As the war drew to a close, the lessons learned from field repairs began to filter into official doctrine. Army Air Forces engineers, studying the improvised modifications that had proliferated across forward air bases, recognized that many of these techniques were superior to the factory-approved methods. New maintenance manuals were drafted, incorporating the hard-won knowledge of mechanics who had never set foot in an engineering school. The line between official procedure and field improvisation blurred, and the distinction ceased to matter. What mattered was that bombers kept flying and crews kept coming home. But the true legacy of the field repairs extended beyond the war itself. The principles of redundancy, adaptability, and improvisation that had emerged from the chaos of combat would shape the future of aviation. Post-war aircraft designs increasingly incorporated multiple load paths and fail-safe structures, features directly inspired by the lessons of World War II, the composite materials and modular construction techniques that define modern aerospace engineering can trace their conceptual lineage back to the mechanics who patched B-17s with scavenged aluminum on frozen airfields in England. In a very real sense, the field repairs that kept American bombers flying during the darkest days of the air war became the foundation for an entire engineering philosophy, a philosophy that values resilience over rigidity, adaptation over adherence, and survival over perfection. There is a photograph taken in the spring of 1945 that captures the essence of this story. It shows a line of B-17s parked on an airfield, their surfaces scarred and patched, their aluminum skins a patchwork of repairs. In the foreground, a mechanic kneels beside a bomber, a rivet gun in one hand and a cigarette in the other. His face is smudged with grease. His uniform is oil-stained. He looks exhausted, but there is something in his posture, quiet pride, perhaps, or simply the satisfaction of work done well, that speaks to the unsung heroism of men who never flew into combat, but who made flight possible. The bomber beside him will fly again. It will carry another crew over occupied Europe, and some of them will survive because of the repairs this man has made. They will never know his name. They will never see his face, but they will owe him their lives, just as thousands of others owed their lives to thousands of other mechanics whose names are lost to history. This is the paradox of field repairs. They were invisible, unofficial, and unrecorded, yet they were essential. They were dismissed as crude and improvised, yet they saved more lives than any single technological breakthrough. They were the work of ordinary men, yet they embodied an extraordinary philosophy of belief that problems could be solved, that systems could be improved, and that survival was always worth fighting for. In the end, the story of the useless field fix is not really about bombers or rivets or aluminum. It is a story about resilience, the resilience of men, of machines, and of a nation that refused to accept defeat. It is a story about the power of improvisation, the value of ingenuity, and the quiet heroism of work done in the shadows. And it is a reminder that in war, as in life, survival often depends not on perfection, but on the willingness to adapt, to persevere, and to keep moving forward even when the path ahead is uncertain. The mechanics who kept American bombers flying did not change the world with grand gestures or dramatic acts of courage. They changed it with wrenches and rivet guns, with scavenged metal and improvised solutions, with work that was thankless and endless and absolutely essential. They changed it by refusing to let steel fail, and in doing so, they helped to win a war. Their legacy endures not in monuments or memorials, but in every aircraft that flies today, in every structure designed to survive the unexpected, In every engineer who understands that the best solution is not always the most elegant, but the one that works. The field repairs that turned American bombers into the war's toughest survivors were never meant to be permanent, but the ideas they represented, adaptability, resilience, and faith in human ingenuity, those ideas are permanent. They are woven into the fabric of modern engineering, embedded in the culture of problem-solving that defines American innovation. And somewhere, on a forgotten airfield in England, a patch of aluminum still clings to the frame of a long-retired bomber, a silent testament to the men who refused to give up, who refused to let their machines fail, and who, in the frozen darkness of a January night, decided that survival was worth one more rivet, one more weld, one more desperate improvisation. That patch, crude, unofficial, and utterly essential, is the soul of this story. It is the proof that sometimes the greatest victories are won not by the weapons we carry, but by the hands that keep those weapons flying.